Good morning, everyone. We will see today the next part of chemistry chapter structure of atom. Last video we had seen the relationship between mass number and atomic number. Today we are going to do the next part, arrangement of electrons in the atoms. How are the electrons arranged in various shells in an atom? Let us take this one as the nucleus. In the nucleus there are neutrons and protons. Around the nucleus there are shells. This first one cell we will call it as the shell number 1, or we can name it as K. Next one we have got shell number 2 or L. Then next we have got shell number 3 or M. Next we have got shell number 4 or N, and so on. How many electrons will accommodate in a shell is given by the formula 2n square, where n represents the shell number. Suppose I have got first cell. So in first cell, how many electrons will accommodate will be 2 into 1 to the power 2 is equal to 2 into 1 is equal to 2. Next we have in the second shell. In the second cell we have 2 into 2 to the power 2, where n value we will put 2 because it is the second cell, and 2 into 2 to the 4 is equal to 8. Third shell we have 2 into 3 because cell number 3. So 2 into 3 we have 9 to the 18. Fourth shell 2 into 4 to the power 2. So 2 into 16 is equal to 32, and so on. In this way we are able to know how many electrons can accommodate in shell number 1, 2, 3, 4, 5, 6, 7 and so on. Next we have that in the last cell we cannot have more than 8 electrons. In the last cell we cannot have more than 8 electrons. Now also the rule that we are going to study up to class 10, in upper class you may study something different, but here we will study that the next cell cannot be filled until the previous cell is filled. That means we can say when the penultimate shell is filled, then only the ultimate cell, the last cell will be filled. But in class 11 and 12 when you go, you will study that no, there are chances of the shell, next cell being filled even though if the previous cell is incomplete. Next we have electrons in an atom do not occupy shell unless all the cells are completely filled. This is what is given in your book. So you have electronic configuration of first 20 elements that we will see. Electronic configuration of first 20 elements. So first we have hydrogen, then we have helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, and after that I will write when I will rub this part. So we have atomic number here 1, atomic number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And when we are doing the electronic configuration, then what we have in the first cell, how many electrons can go maximum? 2. So hydrogen is having only 1, so 1 will go in this, in 2 will go in. For this lithium, where you have got 3, atomic number 3, what we have in the first cell, 2 electrons will be accommodated. In the next cell number 2 or L, 1 will go. In the same way here, 2, 2 electrons in the first cell, second cell remaining 2. Here in the first cell 2 electrons and here 3 electrons. Then in this one 2 electrons and here 4 electrons. Next one, in this nitrogen we have 2, 5. In oxygen 2 in the first cell, 6 electrons in the second cell. Here 2 electrons and then electrons. In neon 2 electrons, then 8 electrons. In sodium 2, then 8, because see in the second cell maximum 8 electrons can be accommodated. So the next one 2, 8 is 10, and but it has got 11 electrons. So 11th one will go in the next cell, KLM. You can write also here at the bottom K, this is L, and here we have M1. Next what we have in this one 2, 8, 2. Then here 13 one 2, 8, 3. 14th one 2, 8, 4. In this way we have got. Now next one, aluminium silicon. Is it visible? Yes, it is visible. Then it is phosphorus 15. So it will be 2, 8, 5. Then sulfur, it is 16. 2, 8, 6. Then next one is chlorine 17. 2, 8, 7. Silicon, phosphorus, sulfur, chlorine. Then we have got argon. Argon you will write 18 and it will be 2, 8, 8. Then we have got potassium 19, 2, 8, 1. See here, about this you will study in upper class 11 and 12, that as per the SPDF rule, orbital rule 1, Hensberg rule principle of, there we are getting told that the orbitals has to be filled, and therefore SPDF 1, that means we will have to fill in this way. In more detail we will study in upper class. Then we have calcium. Calcium is 20. We will study 2, 8, 8, 2. So this is the atomic number serially I have given up to 20 and their electronic configuration, and you must learn them. Next is our valency or valence electron. Valency and valence electron. What is valency? Or what are valence electron? So valence electron means number of electrons that can be accommodated, or you can say in this way, that is present, the number of electrons that are present in the last orbit. For example, here we see in hydrogen only one shell is there, that is only the last cell, so 1 electron. Valence electron is 1. Here in helium valence electron is 2. Lithium valence electron 1. beryllium valence electron 2. So in this way you see the valence electron is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, again 1, 2. So valence electron means number of electrons present in the last orbit. That is we call valence electron. Now what is valency? Valency means combining capacity of an element. That means how many combining capacity of an atom of an element. That means we will see how many electrons are accepted or donated when a chemical combination takes place between different atoms. So as many electrons are donated, or as many electrons are accepted, or as many electrons are shared, that is we call its valency. So we will see there is a rule for valency, that for metals the valency means the number of electrons present in the last orbit. Say why? Because in metals what they do, they lose electrons. So 1, 2, 3 electrons they will lose. So as metals have got 1, 2, 3 electrons only in last orbit. And we have a definition also for metals in terms of electron, that if an element has got 1, 2 or 3 electrons in the last orbit, then they are known as metals. So metals, they have got 1, 2, 3 electrons. So that is their valency and that is their valence electron. So we can say in this way that this side visible, yes. This is what we have for metals and for metalloids. Because metalloids they will share also same. For metals and metalloids, valency of metals or metalloid is equal to number of valence electron. But valency of non-metals or noble gases we have got different. What is that? Is equal to 8 minus number of valence electrons. See here, this one you have understood, 1, 2, 3, 4, this 1, 2, 3, 4. So they have got 1, 2, 3, so that will valency and valence electron will be same for metals and metalloids. But in the case of noble gases and the non-metals, we have got 5, 6, 7, and in noble gases we have got 8. 5, 6, 7 and 8. So in this cases what we will see, the valency will not be equal to the valence electron. Valency will be 8 minus. For example, the valency of nitrogen is 8 minus 5, 3. Valency of oxygen is 8 minus 6, 2. Valency of fluorine is 8 minus 7, 1. Valency of neon is 8 minus 8, 0. In the same way, valency of phosphorus will be 8 minus 5, 3. Sulfur, it will be 8 minus 6, 2. Chlorine, 8 minus 7, 1. Argon, 8 minus 8, 0. Now, next part. Inertness of the noble gases. What is told about the inertness of the noble gases? See, there are 6 noble gases: helium, neon, argon, krypton, xenon, and radon. And these are said to be inactive, unreactive. They do not react. They exist in nature in the atomic form. They are monoatomic and they do not combine with other elements, other atoms of other element. They are found in free state because they are unreactive. They are noble gases. And we have seen example of few. Helium is 2, atomic number 2. Then we have got here next one neon, 10, atomic number is 10. Then we have got here this part argon, atomic number 18. In the same way we have got helium, neon, argon, krypton, xenon, radon. So you will learn the name of all these 6 elements, their atomic number and their electronic configuration. So let me write the of that noble gases also. Wait, I will rub the board first. Now we will see about the noble gases: helium, neon, argon, krypton, xenon and radon. Helium atomic number is 2, of neon it is 10, argon 18, krypton 36, xenon 54 and radon 86. So we will do the electronic configuration. Right, let me add the cell number K, L, M, N, O. So here it will be 2 only, here it will be 2, comma 8, here it will be 2, 8, 8, here it will be 2, 8, 18, 8, it will be 2, 8, 18, 32 and 8. Add and see. 18 and 10, 28, 28 plus 32 plus 8. 8 to 10, 18, hand over 5, 4, 1 minute. Genome, how much it is? 54 only? Yes, 54, it will be here, it will be 18. 54. So, let us add and see once again. 18 and 10, 28, 28 and 18 and 8. Yes, 54. And next we have got, next one is our radon. Radon it is 86. 86 we have done 2, 8, 18, 32, 18 and 8. This one K, L, M, then this one is N, this one is O, this is. So these noble gases, about noble gases also you will learn them. Next we have causes of chemical combination. Everything in this world wants to attain stability. They want to become stable. And the atoms of the element also want to become stable. In order to become stable, they have to obtain the nearest noble gas configuration. So to obtain the nearest noble gas configuration, what do? Either they will donate electron, they will accept electron, that means they will gain electrons, or they will share electrons. So there are 3 ways in which they do or they attain stability: by donating electrons, by gaining electrons, or by sharing. Those that have got, as we had seen earlier here, those, that means the metals, they have got 1, 2 and 3 electrons. So they will donate the electrons and obtain the nearest noble gas configuration. Those that have got 4 electrons in the last orbit, they will do sharing work. And those, the non-metals, they have got 5, 6 or 7 valence electrons. So they will gain electrons and then they will obtain the nearest noble gas configuration. Next we have valency. I have already told you about the valency. Now there are 2 types of valency: electrovalency and covalency. There are 2 types of valency: electrovalency and covalency. What is electrovalency? As many electrons are lost, as many electrons are donated, or as many electrons are accepted, that is known as electrovalency. So you will define electrovalency in this way: the number of electrons accepted or donated during a chemical combination by an atom to the other atom is known as electrovalency. For example, we have seen the case of sodium. Sodium, it is having atomic number 11, and when we are doing electronic configuration 281, so it will donate 1 electron. So its electrovalency will be either 1, or you can write 1 or 1 plus. In the same way of magnesium, it is 12, atomic number is 12, so electronic configuration 2, 8, 2, so its electrovalency will be 2, or you can write 2 plus. In the same way, aluminium has got atomic number 13, so its electrovalency will be 3 or 3 plus. Next we have, this was the about the metals. The metals, what they do, they lose electron. So I was telling about the electrovalency of sodium, magnesium, aluminium. These metals, they donate. They donate electron, 1 electron, 2 electron or 3 electron. So electrovalency will be 1 plus, 2 plus or 3 plus. In the same way, the non-metals, they gain electron. So for example, chlorine 17, 2, 8, 7. So they will need 1 electron. Chlorine will need 1 electron. So what will be its electrovalency? 1 or 1 minus. In the same way, oxygen requires 2 electrons to fulfill its octet, to obtain the nearest noble gas configuration. So electronic configuration of oxygen is 2, 6. So it will require 2 electrons. So when it will accept 2 electrons, its electrovalency will be 2 or 2 minus. In the same way, nitrogen 7 atomic number 2, 5. So it will require 3 electrons to obtain its nearest noble gas configuration. So its electrovalency will be 3 or 3 minus. Next is our covalency. What is covalency? Covalency means, I told you 3 ways, either they will accept or they will donate, and the third one is about sharing. So when atoms of the same element or atoms of different element, what they do, they share electrons, then such type of valency is known as covalency. Covalency means sharing of the number. You can define in this way covalency. The number of electrons, or you can say the pair of electrons, that will be better, because for one pair we write 1. So the pair of electrons shared in order to obtain the nearest noble gas configuration is known as, we can say, as covalency. Or we can say to fulfill their octet. For example, let us see chlorine one case. Chlorine, what the atomic number? 2, 8, 7. So if chlorine will combine with chlorine, then it will share 1 pair of electrons. See, in this way you will study in upper class 10, you will study about this chlorine. See, it will share 1 electron with this other chlorine atom, and again it will share this 1 electron with this other. So this is Cl, single bond Cl, and finally it forms Cl2. So this how many electrons are shared? This chlorine shares 1 electron, and this chlorine also shares 1 electron. So one pair is there. So in this way we can say that covalency of chlorine is 1. In the same way of hydrogen, covalency is 1, and many more are there. You will study about them. For example, we have of nitrogen. They will share how many electrons they will share? Nitrogen. See here, nitrogen I have already written. 1, 2, 3, 4, 5. Again another one, 1, 2, 3, 4, 5. So it is sharing 3 pair of electrons. Okay, so the covalency of nitrogen will be 3. In the same way, the covalency of carbon will be 4. Next we have isotopes and isobars. What are isotopes? Isotopes are the atoms of the same element having same atomic number but different mass number. Isotopes are the atoms of the same element having same atomic number but different mass number. For example, hydrogen, we have got 3 isotopes of hydrogen: protium, deuterium and tritium. Then we have got 2 isotopes of chlorine, 35 and chlorine 37. We have got 2 isotopes of uranium, uranium 92, 235, and uranium 92 and 237. We have got 3 isotopes of carbon 6, 12, carbon 6, 13, carbon 6, 14. Similarly, we have got isotopes of neon. So what we will see, isotopes are the atoms of the same element, but having same atomic number, but their mass number is different. So in this way you will learn the definition of isotopes and their examples. Next is isobars. What are isobars? Isobars are the atoms of the different element. Isobars are the atoms of different element having same atomic number. Having different atomic number but same mass number. Isobars are the atoms of different elements. For example, we have argon and we have got calcium. Argon is having atomic number how much? 18. And calcium how many? 20. 20. Atomic number 20. See, but mass number you see of argon it is how much? Here it is 40 and this argon is also 40. So isobars are the atoms of different element. Isobars are the atoms of different element having different atomic number but same mass number. See here atomic number will be same, mass number will be different. Here mass number will be same, atomic number will be different. Next we have that all the isotopes of an element have got identical chemical properties. All the isotopes of an element, for example, the isotopes of hydrogen are these three, chlorine are these two, uranium these two, carbon these three, then neon. So we are saying that all the isotopes of the same element, of an element, have got same chemical properties. Why they have got same chemical properties? They have got same chemical properties because their atomic number is same and the chemical property of an atom is dependent. The chemical property of an atom is dependent on its atomic number, not on the mass number. So their chemical properties are same because the isotopes have got the same atomic number. So their chemical properties are same. But again we will study in the next part that the physical properties of the isotopes of an element are different. The physical properties of the isotopes of the same element are different. Why they are different? Because physical properties is dependent on the mass number and not on the atomic number. And since they have got different mass number, so their properties are also, physical properties are also different. Next we have radioactive isotopes. What are radioactive isotopes? The isotopes which are unstable and emit various types of radiations. Those isotopes which are unstable and they radiate out various types of radiations, they are known as radioactive isotopes. And we have got some of the radioactive isotopes and their uses. For example, the radioactive isotope of uranium-235. Uranium-235, I have written it. Uranium-235, the radioactive isotope of uranium-235 is used for the purpose of generation of energy in the nuclear power plants. Next we have got radioactive isotope used in the tracers in medicines to detect the presence of tumors and blood clots, and that one is sodium-24 and arsenic-74. Sodium-24 is used to detect the presence of blood clots, and this one arsenic-74 it is used to detect the presence of tumors. And next we have got radioactive isotopes of cobalt. They are used in the treatment of cancer. Then we have radioactive isotopes of iodine. For example, iodine-131. It is used to determine the activity of the thyroid gland, which helps in the treatment of the diseases like thyroid. And radioactive isotopes are also used in the industry to detect the leakage in the underground pipelines, gas pipelines, water pipelines, and that is with the help of the Geiger counter. Actually, these radioactive isotopes in NCERT book it is not given, but in our SCHAN book it is given. So I just told you all the name of the radioactive isotopes and then the uses of each one of them. So this chapter is over. You will study nicely, go through the videos again and again. If you are unable to understand, see them once or twice or stop them again, go backward and watch them properly, and whatever the definitions have been told, you will try to learn them. Okay, thank you.